I would like to welcome you this evening to the third lecture of the 2012 season, which is the 10th season now of the Carnegie Huntington Annual Lecture Series. And it's a pleasure for me to introduce this evening's speaker, Dr. Barry Madore. Barry is a renowned astronomer with a very broad range of interests. He's worked in almost every field in extragalactic astronomy and has made fundamental contributions to our understanding of, for example, star formation in galaxies, the way galaxies evolve, galaxy evolution. He has made a study of peculiar galaxies. In fact, he's one of the experts on peculiar galaxies, by which I mean colliding galaxies, ring galaxies, companion galaxies, and he and Halton Arp many years ago cataloged large numbers, the largest numbers of these peculiar galaxies known, and he's been following up and trying to understand the nature of these objects ever since. He is a co-founder of the NASA Extragalactic Database, NED, and this database now contains information for 170 million extragalactic objects. Essentially, everything that anyone has measured having to do with an extragalactic object, either from space or from a ground-based telescope, at any wavelength, at any resolution, whatever is known goes into this database. And literally, it has changed the way astronomy is now done. Change the way astronomers do astronomy. It will never be the same. He is a co-investigator on NASA's GALAX mission. This is a galaxy explorer to study the universe in ultraviolet radiation. And one of the areas, perhaps, where he's best known is the area where I've collaborated with him for now over 30 years, and that is the study of what are called Cepheid variables and the extragalactic distance scale. But none of this is what he's going to talk about this evening. One of Barry's other interests is in the philosophy and the nature of science. And so I promise you that this evening's lecture is going to make you think. And I present to you Dr. Barry Madore.
Any sufficiently advanced technology is indistinguishable from magic. Arthur Clarke said that. Nothing in the universe is self-evident. I said that. You can be in my dreams if I can be in yours. Bob Dylan said that. So where does that leave us? Somewhere between a dreamy, blissful ignorance and a shadowy, incredible magic? What I'm going to try and convince you of, that's not such a bad place to be. Cognitive astrophysics. What is this talk about? It is about magic. It's about shadows. It's about words and linguistics. So listen very carefully. It's about astrophysics. And most importantly, this talk is about 45 minutes. But there are three key phrases I want you to take away. Words that may not be familiar, but concepts that really are quite simple. Those three are reification, and we only have to go to Genesis for a complete study of that. It's how you name things. What are the consequences of naming things? The other is what's called the multi-wavelength inverse problem. And that's just code for what astrophysicists, astronomers, and cosmologists do every day. We tried to solve that problem. And it was a problem that was elucidated first by Plato, and I'll show you the path through that. And then there's this thing called cognitive closure, which most of you have not heard of. And it's described in great depth in a book called Conversations with a Cyborg. Well, nothing is self-evident. You know, I don't think you will ever be at a lecture or have a lecturer give a talk where they just put something up on the screen and you look at it and you understand it. You won't have a speaker come in and put up equations and have the audience just nodding knowingly and understanding. Nature has provided us with the second most important gift of evolution. That's language. And language is the intermediary, it's the way in which we interpret everything about us, whether it's an equation or a photograph of an object. It's the path that makes us different and allows us to understand the universe. But it may also be the greatest barrier for us for getting final understanding of the universe. And I'll try and make it fairly clear why it has these yin-yang, positive, negative aspects. But in terms of words and phrases, here's all the information you need, but quite often it's presented in a way that it's much more easy to understand. And throughout this talk, I'm going to be throwing things at you that you should know, or you probably do know, but in a way that I hope forces you to think a little bit harder. Everything's there. Wittgenstein was brought in by into Cambridge, the head of the philosophy department in Cambridge, because he was certainly one of the most brilliant men of the 20th century. And one of the phrases that he had was, whereof one cannot speak, thereof one must be silent. Well, that probably didn't help. But a contemporary of his, T.S. Eliot, who was a poet, a playwright, and a literary critic at the same time, he had moved from the United States and was living in London at the same time as Wittgenstein, wrote a play called Sweeney Agonistes. And Sweeney goes into the pub one day, and he's talking with his friends, and he finally says, look, if I'm going to talk to you, I've got to use words. Right. This is the common man's approach to what Wittgenstein had said. One word that's not used very much in physics and astronomy is the sublime. This is something that takes you between a feeling of awe and utter terror. This is an entire system of stars and gas that's exploding. You have no idea how large this thing is and the destructive power of this event. If you did, you'd be cringing in your seats. The question is, can we really understand such things on such enormous scales with enormous force over times that we have no direct experience with? Well, let me talk to you a little bit about the multi-wavelength inverse problem. That is, how we do astronomy. Plato introduced this concept with his allegory of the cave. And in it, astronomy graduate students were chained to their seats. And all they could see were the postdocs and faculty having a great time behind them, And all they were allowed to see was the fleeting images of people prancing in front of the fire. Now, that was their view of the universe, this flat, monochromatic silhouette of what the world was. And Plato was trying to attempt to show that there was probably something greater out there, unlike this corrupted version of reality that was cast on the walls. But eventually, one of the prisoners, one of the graduate students, gets her way out, climbs up the stairs, walks out into the edge of the cave, and this is what she sees. Frozen in time. Now, time is here to stop everything from happening at once. You know that. But when you're looking at the universe, exactly the opposite happens. You've got the entire age of the universe projected down onto through the sky. There's no sense of time, but there's history. And there are these enormous, strange objects out there that we are trying to invert the process, take the thing that has been projected up on the wall, take the thing that we see on the sky, and somehow invert that to the point that we understand what the object is in three-dimensional space, and even worse than that, understand what it is as it moves through time, what its origin was, what it will become. Whether we apply that same type of thinking to individual objects, stars, galaxies, or the entire universe, that is the inverse problem. Going from something that's flat into something that's dynamic and three-dimensional. So we have this multi-wavelength problem. We have this reification where we have to go out and classify things and give them names in order to study them. And here's another example of the inverse problem. This is a beautiful piece of art that this thing up here in three-dimensional space, in its shadow form, is quite recognizable. We can give it a name, or it's a motorcycle, or over here it's a ship. But what it is in three-dimensional space, and this is the problem with the inverse problem. This is the problem with the problem, is that in going from this to this, we're trying to construct the three-dimensional thing. And this piece of art, I've got to tell you, it's sort of hard to see it here. It's made up of welded pieces of spoons, forks, and knives. So if you think that you can name this object, and then go invert it and go back into three-dimensional space and get that configuration of things, and even conceive that it would be made of something as mundane as knives and forks and spoons, then you see the problem, that there's no uniqueness in this. There's so many things that could be out there. We only see this one shadow of it. Now, we're really good at picking out information in seeing forms and giving those forms a reality of sort. I think everybody can see the outline of this dappled Dalmatian moving through the leaves, heading towards the tree. You can see the shadow in the leaves. We're really good at picking out information when there's very low signal to noise. This is just a black and white picture. And yet we can see details in there that make sense. Well, what our young Adam here says, now, that should clear up a few things around here. So reification is the act of attaching a name to a set of observed properties, thereby creating an object. It's a little bit different than starting with the object and giving it a name, but this is creating an object based on the properties. And the caveat is that you can do this whether the object exists or not. Now, in Genesis, the animals were just brought in one at a time, and Adam gave them a name, and that was it. And this is Adam over here. And it's interesting to see not only what he decided to name, but what he didn't name. This area right in here, the Katplatz, or the Hundspots, the space between a cat and a dog. It really matters to the dog how far away the cat is. And from the cat's perspective, it also makes a big deal, but it never got named. And you know that Adam's going to be in trouble as soon as he goes in the house, because he didn't name the eaves. So we have the creation of names, the filling in of spaces, even when they don't exist. And now I'm going to go out on a limb, so to speak, and talk about something that I believe you all think exists, you've all seen them, and I will make the case that they do not exist. This is entitled, you can guess it, Still Life. It's one of those same projections that, depending on your perspective and depending on how the lighting occurs, you get to see the message. Here's my message. Just down the street near Wilson and Arden Road, you can find this tree overhanging the street. And on a sunny day like today, down on the road, you can see what you would call a shadow. What you would call a shadow. What am I talking about? It's a shadow. Well, if you get a little bit closer and take a look, you see these little circles inside the shadow. Well, those are just gaps, right? No. Those are individual images of the sun cast by the pinhole camera effect of the leaves coming together, allowing a certain amount of light to come through and shine an image of the sun here and here and here and here. Pinhole cameras do more than just image the sun. There is an image of the entire sky around each one of these images of the sun. The pinhole camera images the sky. It turns out that the sun is very, very bright. So it's very hard to see anything else in this image, this multiple pinhole camera image of the sky. But these are images of the sun. Here's a blow-up, and you can start to see, again, all of the circular little areas which are individual images of the sun. Well, what about the rest of this stuff out here? There are hundreds of images of the sun. They are all overlapping out here. It's only these ones that make individual pictures. And so what's so interesting about that? The interesting thing is that if you realize that the physics is in the solar images, not that there's no information in the thing that you call the shadow, then you can't do what I'm about to do. See here, there's a nice circular image about, 6 or 8 inches in size. There are some smaller ones up here, maybe 4 or 5 inches. What I can do with that information is that I can project back, and for every inch, I can tell how far away the pinhole camera was. So this thing is about 80 feet away. This is about 40? And so there is a tree behind this image, around sunset, I would imagine, because these images are quite circular, so the sun is coming in pretty much perpendicular to the wall. And I can invert what I don't even see. I can tell you that there is a three-dimensional object behind the person that painted this picture. So I can use information, I can use physics, but not by thinking about shadows, but by thinking about the images that those pinhole cameras produced. The shadows don't exist. Renoir was painting a picture behind himself. See the little shadows here? There's a tree that's probably not more than 20 feet away from him behind. And you can see there are other trees, so it's not unexpected that there might be one. But when he painted this picture, he was actually telling us what was going on around him and behind him. Now, can you see? I have reprogrammed my brain. Wendy can tell you this, that when we're walking down the street, I'm looking at circles all over the ground. I'm looking for sunspots inside the circles. And look at them. Tell me that you can't see the sun now shining through the tree down onto the ground, where now, by changing the way in which you look at the problem, you can now see physics on the ground, physics in action. And see, they are different sizes. There's some fairly large ones over here from high up in the tree and some smaller ones closer in. Just in case you didn't believe me, here is reprogramming your brain. This is the same situation of a tree putting light down onto the ground during a solar eclipse. So each one of these things is now an image of the sun with the moon blocking most of it. It's not some aberration of the camera. This is the picture on the ground. And here it is, a little bit later, when the sun is right over, or the moon is right over the disk of the sun, and it's an annular eclipse, so you see the ring around the sun. Tell me now that you can see shadow. There's no shadow there. Well, if there's no shadow there during an eclipse, then I'm betting you there's no shadow there when the sun is out by itself. So what were you thinking? That's the title of this, this piece of art. That silhouette is from all of these little pieces of plastic that are there. So depending on how you view the world, depending on what the illumination is of your world, you will either get the message or you won't. So a great deal of what we do depends on our perspective on the world and how we represent and what the universe presents to us for us to interpret it. Okay. So shadows, we have the creation of objects. We have some of them that are non-existent. This now, I challenge you to use your brain to figure out what it is. Well, it certainly looks like some sort of topological map. These lines are in there because they're all at the same level. And it might be, I don't know, Bryce Canyon or the Grand Canyon. It might be a radar ranging of Venus. It might be some simulation of some canyon on Mars. But it's none of those things. These are positions, and the elevation is intensity, how bright something is. So this is a very bright region. These are very faint regions down here. And what I'm going to do is slowly reveal what this picture is by flooding the canyon, if you like, from the bottom up. So I'm going to reveal the lower bits first, bringing up the image, Can you tell what it is? Can your brain get around this image? That if this is what the universe presented us with, that you would know what we are dealing with? I don't think so. But here it comes. Oh, oh my gosh. Would you have known that this bright area was a wall, and this was a picture, and this was this young woman's hair, and here's her nose and her chin, and so on? What an amazing sort of thing to see, but it's a little bit frightening that there may be thousands of things out there that are coming to us in that form. And we just haven't the imagination, or maybe even the cognitive skills or mindset to be able to interpret them in the way that this picture tells you that that information was there. All right, one step from the ridiculous to the sublime. This is a picture of where Napoleon was buried on St. Helena's Island. And I want you to remember that picture. Everything about it. Okay? Because I'm going to, when we get back in a second, this is my feeling of what the sublime is. This is a galaxy, another galaxy, where there's star formation and there are dust lanes, but it's something that is really hard to fully understand. But we're going to take a break, and I'm going to show you some magic, and then I'm going to ask you to try and remember what that picture was, because what I'm going to do is when I show you the picture again, for the first time, you will not be able to see it again the way you did the first time. All right? This is called aponesia, the inability to forget something. Most of the time it's called learning. But there are situations where once you've seen something, once you've learned something, you may not be able to see it again the way you did, and maybe the way you see it this time, the first time you see it, the one that's stuck in your mind, is the wrong way. But you can't get rid of it. You can never go back and see the universe once somebody has taught you what you're expected to see. So if I could have the lights for a moment. I would like somebody to pick a card, any card. All right. Well, you're aggressive. All right. Now you can look at it. You can show whoever you want what it is. Are you happy? You can answer some questions about it. Yeah. No. No. Is it a red card? Yes. Well, if I had been a black card, I would have known it was a red card, right? Is it even, the number? Is it the 8 of hearts? Yes?
Are they all 8 of hearts there?
Well, all right. That's one possibility. Fine. Try your hand at it. That one? Okay. Yeah. Is your card a red card? It is. Is it even? No, it's odd. Yeah, it's odd. Okay. Is it the 7 of diamonds? Ah, well, maybe there's only 2 types of cards in there, right? I mean, I don't want to take us away from the talk for too long, but I really can't resist doing one thing. I need 3 people who are willing to come and do this test. Quickly. All right, 6. Come on. Pick a card. Don't show it to me. Pick a card. Okay. All right, I want you to pick a card. All right, you get one left. All right. Now, memorize them, put them in the envelope. Oops. Your card? No, don't tell me. I want you to take it out, and I want you to put a little red check mark in the upper right-hand corner. All right. Now, what I'm guaranteeing you here is that you will never be able to figure out what I did. I don't care how long you watch me do this, and put it back in the envelope and then seal it up. Because I learned this trick from a philosopher. Now we're going to, all right, yeah, hold on to it, just so I don't screw up. You can sit down, and then at the end of the talk, we'll figure out what it is. But what this philosopher found from this magician, who did this trick to other magicians, was that the other magicians couldn't figure it out. And he finally told the philosopher just before he died what he was doing. And he said, every magician knows how to do this. Everybody has a variation on it. Everybody has 2 or 3 ways of doing the same trick. And that's the trick. He learned 5 different ways of doing it. And so when the magicians were watching him, he'd switch to the other trick. And so they never knew which one he was switching to. All right? So it may be that the universe works that way, that we figure it out, but it does the same thing 5 or 6 different ways. And we think, well, we solved it. Okay? Maybe. Okay, let's bring the lights down. We'll find out whether that trick, where everything's hidden, can be solved by a computer. All right. One step from the ridiculous to the sublime. Did you remember what that picture was? Well, right now your whole life is going to change. Because there is Napoleon sitting in between the trees. But now you can't not see him. You can never look at that picture again and see it like you saw it the first time. What have you lost? Because when you look at this picture, oh my goodness, there it is. All right? So maybe you've gained something, but maybe you've lost something. But the fact is that once you're in this space, you can't get back. So I don't know, in the process of learning astrophysics and teaching astrophysics, what sort of damage we're doing in the process as well as moving on. It's not to say that it's a bad thing to do, but it would be really nice if once in a while you could back off and really believe that there are no shadows. Aphanesia. All right, how about this? This is a petri dish. It's got some chemicals in it. And, this part up here, if you just looked at it, you might say, well, there's sort of splashes and stuff going on in there. But in fact, it's a very, very unusual chemical reaction known as the Borisov-Zhabotinsky reaction, which nobody believed because they were Russians. It was in the 50s. But, and this is the sort of thing that we have to deal with all the time in astronomy. You get this picture of something out there, and you're trying to understand, how does this thing evolve in time? What is it actually doing? What is the physics underlying these structures, if that was a galaxy? Well, here it is, another experiment, same chemicals. And look at the incredible structure that this chemical reaction is able to self-organize itself and produce these very complicated structures. And when you look at them, it is an amazing thing to watch. These little rings are rotating around and they're moving out, and it's a glorious thing to observe. But it does it all by itself. Well, here are all the chemical reactions that go on inside the Belousov-Zhabotinsky reaction. Now, it's sort of interesting. You see, you put in Br minus, and down here, Br minus comes out, and you put in some of this, and it comes out over here. And this is what's called an autocatalytic reaction. You know, a catalyst is something that enables a process to go ahead, but in the end, it's still there at the end of the process. So I would claim that there is no way on Earth that looking at these equations, you could predict that that's what would happen. Similarly, it's really hard to imagine going from this picture, that even if you had the whole time sequence, to predict from these observations what the underlying chemical reactions were. So there's this cognitive dissonance between the chemistry and the manifestation of the chemistry in a two-dimensional situation. But buried down in here, at a level that you can't read, but I can, are the rate constants, telling you how fast each one of these equations is going. And without seeing this and without seeing that, just looking at these rate constants down here tells me that that is inevitable. Now, I can explain it to you later, but if it doesn't depend on the chemistry, then it tells me that any situation that has rate constants like this, whether it is electric waves moving across the heart, or whether it's neurons firing across the surface of the brain, or whether it's slime mold aggregating underneath a tree stump, all of which have the same characteristic of time constants and autocatalytic. They will all produce these same geometric forms. In fact, they do. I mean, there are slime molds that make these little rotating spirals and things. When you have an epileptic fit, those are waves that are propagating as spirals across the surface of the brain. And when your heart requires defibrillating, the reason is that pulse that goes out to make the contraction actually gets broken and turns into one of these spiral waves rolling and rolling around on your heart, just causing absolute chaos over the entire muscle. All of those things are down here. Well, what about our ability or inability to see things in the universe? Here is a very much blown up image of a galaxy taken with the Hubble Space Telescope. Not particularly impressive at this stage, but you know, we have a name for it. We've reified it. It's a spiral galaxy. You can see those spirals. But if you go way back out, oh my God, you know, this thing, the background of it is this other galaxy. It's a companion, but it's the intermediate stage where the really exciting thing shows up. Here's the galaxy. Here's this other galaxy, which is behind it. So this galaxy is not small because it's very far away. It's small because it's intrinsically small. But there are only a few galaxies like this where you've got the right line of sight. Look at all this stuff out here, all this dust, which is silhouetted against the face of the background galaxy. Well, there's probably stuff out here if it's over here. But we certainly never would have predicted, based on this image, that the galaxy was maybe 4 times larger than it really is, and that there is all of this dust and gas far outside of it. So it's only by, again, that lighting, the particular geometry which we happen to be in, that we got to see this. But it's not built into anything that we knew or would have predicted before. So we sometimes get lucky. Look at this one. Here's the little spiral that we would have seen, but look at the enormity of the other material going all the way out, and there's pieces of it over here and pieces of it there. these things that we call galaxies are much more complicated and much larger in many cases than we ever expected. And it's often by pure serendipity that these sorts of things are revealed. Well, here's a system of galaxies. This is the core of what's called the Virgo cluster. And this image it's just in black and white, but it's very, very, very deep, to the point that we're seeing surface brightness features that had never been seen before. Which then, well, here's where these black areas are where the optical galaxies are that we knew about before, the ones that we reified, the ones that we cataloged, the ones that we have positions for. But what is this outline? Is this now one galaxy and these are just subcomponents of it? The same thing over here. All these other little bits and pieces, do they belong to this larger system, which seems to go on forever? What is this elongated structure? Is that a galaxy, or do we call it something else so that we can claim that it is something else? Or is it really just a feature of this bigger object? These are all important questions because they bear directly on how we go about modeling these things and whether we consider them to be separate entities or whether they are part of a process. And maybe the process is more important than the objects. And so there's now sort of a mindset change here in moving away from the things which we give names to and backing off and saying, there are no things there. There are only these ephemeral properties of a process. Okay. This is our dog. This is Bailey. And when he came out of the swimming pool and was drying off, he said, "What's an electron?" I felt obliged to dry him off. And as I walked over to him to pat him on the nose, I had been shuffling my feet, I'm afraid, and a spark went off and just took him right on the nose. All right, so Bailey now knows what an electron is. And for the next 10 or 15 minutes, I went through with him about the Schrodinger's equation and electrons being stripped, and that's what I was doing as I was walking across the room. And he looked at me, he said, "Oh, this is a friend of his, and it's called bonding." And Bailey said, "You've got me all wrong. I can't speak. I can't read. I don't understand what you're saying. I don't really know what an electron is, and I never will." You think, oh, poor dog. He's never going to solve those equations. He's never going to he's never really going to understand what an electron is. Well, welcome to reality. You may feel sorry for the dog, but he can equally well feel sorry for us because he can smell things that you can't. He can smell things thousands, maybe a million times fainter than you will ever experience. He can smell things that he really likes, like rolling in some dying, dead carcass which is wonderfully sensational for him. And we will never be able to experience that. We are cognitively closed to knowing what it's like to be a dog, much as he's cognitively closed to knowing what an electron is. Well, isn't it sort of strange that 125 pounds of full-bore Labrador is something that we cannot understand, and yet we think we understand the rest of the universe at the large scales, and that we think we understand the things that are smaller than a dog, down at atoms, and we probably do to some degree. I mean, people have been working on it for a very, very long time, but it does raise the possibility that on other scales, there are things that we are similarly cognitively close to. that we will never experience them. We'll never experience the expansion of the universe. We can pretend that we can see aspects of it that are consistent with it. But we'll never really experience it and see it. It looks the same every time we look up there. Right? We can measure things, and we can model things, and we can make experiments of a limited degree. So suppose you were born on Venus, and you were exploring the universe. And the first thing that you could do was build a radio telescope, and you knew that there was a lot of hydrogen, and there was this hydrogen line because you'd experimented in a laboratory. And so you built a radio telescope to look at neutral hydrogen. And you point it up in the sky, and you say, whoa, look at this group of things, these smoke ring-like things. They're made out of hydrogen. They're rotating. They're moving around here. Pretend this is a shadow, and it's just gone. Just forget about that big blob in the center, because I'll explain what it is. It's not neutral hydrogen. Just concentrate on these ones. Well, on Venus, they do know about gravity. And for these things to be rotating in rings, there has to be something to rotate around. But you can't see it. So they've discovered dark matter. That's wonderful. They've discovered dark matter. And then they notice that there's nothing sitting in here, especially none of these guys. This thing hasn't been observed yet on Venus. And they say, oh my God, not only is there dark matter inside these galaxies, but there must be dark matter inside here because they're moving around in their orbits around this area which is empty. So they build an X-ray satellite. Let's move all the way from the radio and get some congressmen on board, and we'll build an X-ray telescope, and we'll look at it. Maybe it's some other form of hydrogen, hot hydrogen. Well, lo and behold, boom, there it is, there's the signal. Something really hot, millions of degrees. Oh, we know now what dark matter is. It's just hot hydrogen. Until somebody points out, well, no, because these holes didn't fill in. So now you have two types of dark matter. You've got this stuff here and something else in there. Well, okay, let's split the difference, build a space telescope in the optical and put that up there. And that would have been the picture you saw before of all those very faint structures of things that they had never seen before, stars. Stars would fill in the holes here, and there'd be a whole flurry of new objects, elliptical galaxies we call them, which are just pure stars, filling in the center. We've solved the dark matter problem. No. Because if you add up all the mass that's in the stars and all the mass that's in the gas and all the mass that's in the hot gas, it's still not enough. So they would have been just back to where we are, but they would have had an entirely different history and path of discovery. They would have discovered dark matter, which they thought they had discovered, and then they would have thought they'd fixed it, and they hadn't. So we're in that situation now where we don't know what it is, but we use the same logic of balancing what we see against gravity to know that there must be this dark component out there. So we have all these words, and we have all of these things and these processes and reifications. Is there some way of going back and forth between the words that we use and the mathematical and descriptive tools that we have? Here is a power spectrum of galaxies over, well, these are wave numbers, but it's telling you how far apart things are. There's no structure in this whatsoever. There's no little sign that says, over here, triples, over here, quadruples, over here, clusters. There's nothing in there. And so it starts to make you feel a little bit queasy about just how important these words are that we use to describe situations out there, because somebody said, well, there's a pair, there's a triple, they're interacting and they're gravitationally bound, but are they of fundamental importance? Similarly, here's another representation of, in this case, it's wavelength along here, well, frequency, and brightness of the source. And this is the image. This is just one little dot over here in this very wide-ranging spectrum. It's called a spectral energy distribution. But this picture is the basis of what we think galaxies are. It's the basis of this Hubble sequence of typing things to try and figure out what are these things, what are they made of, and how do they evolve. But it's really hard to go from here, where you're looking at the galaxy over many, many wavelengths, which is very important because there are all sorts of processes going on, to predict what this thing would look like here. And it's really hard to go from what this thing looks like to what it would look like at other wavelengths. Well, that's research. But it does give you pause that for better part of a century, this is all we knew about galaxies, and this was our basis for predicting and understanding how these large systems evolved. Here's a similar power law for the whole universe. This is when the universe was very young, and you see all of these parameters here where behind the interpretation of these observations, and it's really irrelevant what that is, but it was derived from this map over here, and it gave you this stuff over here, and in order to understand it, you had to have a model over there, which has a lot of parameters in it, which are physically motivated. It's good stuff, and here are a few of the 20 or 30 parameters that are needed to fit the data. But whether you could actually go from here and say, that's what it should look like, or go from here and looking at it and say, this is what it should be, it's not in our minds anymore to be able to do that. there has to be an intermediary of the computer. Okay. Physics is based on reductionism. That you take big things, big complicated things, and you break them down, and you break them down, and you want to find the elementary particles, you want to find the basic equations that describe things, and then you build it back up again. And again, when you have a picture like this, you don't really know what the time sequence is. Are these elf-like scientists cutting up Santa to try and figure out what he is? To reduce him down to basics, to understand what the fundamental elementary particles of Santa Clausism is? Or are they putting Santa Claus together? Are they building themselves a model of Santa Claus? I don't know. But in the 20th century, Karl Popper suggested that for every observation, there are 10 really smart people. Theorists will be able to provide you with self-consistent models that will fit your data all the time. So what you want to do, according to him, was find an observation which eliminates theories. Don't wait for them to try and figure out. Preemptively strike the theorists with an observation that will falsify the theory. Well, that seemed like a pretty good idea because most of those theories were written down, they had firm predictions, and they were simple. So you whack them one with something that they can't predict, and the theory's out. Well, as I was suggesting, in interpreting the background radiation from the early universe, things aren't quite that simple anymore. We have a lot of physics, but in order to attempt to formulate an interface between the physics and the observations, we use simulations. We don't just use words anymore. We use computer simulations. Now, these are very, very complicated things with many, many knobs. And they're like Canadians. They sort of speak like us. They walk among us. And you can't kill them. These programs are really good at sidestepping any falsifiability. You say, well, here's a new observation. You didn't predict that. Oh, we'll turn the dial. Oh, it's fine. Well, that is fine, but does that really constitute true understanding? And it may be that these computers, at some point, whether they're attached to the side of your head or in orbit somewhere because they're so big you can't build them on the ground anymore, they'll probably talk to us. And we can ask them questions, and they will do our bidding. And then you'll say, well, okay, I wanted to know about how galaxies formed. And they'll come back and say, okay, we know. And you say, well, come on, tell me. And they say, you're too stupid. I say, no, come on, break it down into words that I can understand. They say, okay, if you insist. And up comes the line printer, and you're reading as fast as you can, and it's still going, and you're trying to read it. And you say, look, whoa, slow down. He said, well, you asked for it, and it's printing and printing and printing, and you're reading it, and you're understanding it, but it's still coming. And you say, how long is this going to take? Oh, about 1,000 years. Well, I mean, at what point do you say, enough, okay, you understand it, I can't. And maybe that's where we're heading, where there will be things that will be understood. And in a sense, does it matter if only one person in the world understands something? Do we declare victory there? And what if you just take it down a notch and it's a machine that understands it? Is that okay? Well, maybe it is. So we've opened up this Pandora's box of computing, which is now no longer falsifiable. It might be impervious to any sorts of questions we can ask it. It might come back with an answer. But we may not be able to fully appreciate what those answers are. Now, how many people here know, you've heard about Pandora's box. Did you know that the pre-Raphaelites changed it to a box? It was an urn. It was Pandora's urn. Anyway, they thought it would look better as a box that you could open up. Well, it unleashed all of this misery on the world, computers included. But one thing remained in the box. Does anybody know what it was? Hope. Hope, yes, hope. We have hope. For what? Well, let me go back to Alfred North Whitehead. He's the one that brought in Bertrand Russell. He was his mentor. And then he left and he went to Harvard, left Cambridge. And he took up education. And what he said were the three most important aspects of education over a person's life. And I take that to mean the three most important aspects of research because it is just continuing education. The first was precision. And that is when you just go out into the world and you find the individual things that are out there and bring them back, and you've enumerated them. You've gone on your fishing trip, you've found all the things you've been playing in the backyard. That was part of it. That's part of learning what the world has to offer. The next was generalization. You've got your little piles and you've named them, the reification. And you're trying to do the inverse problem, and that is generate understanding. And so you categorize and you classify and you produce equations and theories. How you want to live your life with all of these things around you so that you can protect yourself, you can predict what's going on, whatever. But that's also what's done in science. Do you know what, you knew what hope was. Do you know what the third aspect of a fully rounded education was? And he had this first, and I think it's something, and he never said that you do one or the other or the other. You have to have all of them going. You had to have the precision, you had to have the generalization, and you had to have romance. Of course. Why else would we be doing this? It's fun. It's what drives us, which takes us in the mornings and brings us into this field in the beginning. It is the romance, the joy of doing science. So I would say, give that to the computer. Let the cyborgs have this one. But they can't touch romance. And there is no computer that's going to understand when you say that this is a picture that's entitled Young White Trash with with seagulls. Okay, so we've got the romance, we've got the hope, and this is what was up to begin with. That ours, not the robots, not the cyborgs, ours is a conversation that began in the primeval forests, extended and made more articulate in the course of centuries. And I can't tell you whether this is the curtain coming down or peeking out on the audience, but I thank you for coming tonight. Could I ask you to open the envelope? What?
It is.
There's more. Which card did you check? And there's more. How did the computer do it?
Will you entertain some questions?
Will you understand them?
Yes.
At the risk of having lost you or not having paid attention at all and missed the entire point of the lecture, I'm wondering if the questions about the solution or non-solution to dark matter came out of the recent stuff at CERN, the experiments at CERN.
I haven't heard anything definitive about the detection of dark matter particles from CERN. They're looking for elementary particles that are predicted by theories of fundamental particles, and we may hear within the next year, but you will definitely hear if anybody makes the definitive discovery of what the dark matter particles are, what the Higgs boson's mass is, or what the actual origin of the dark energy is. I mean, that will just be that big on the cover of the LA Times. So, yeah.
I've heard the paradigm of life as a video game, and we're sort of getting really good scientifically at playing the game and shooting down the aliens, but maybe not knowing the underlying circuitry. Do you think as high energy physics might have a low energy tail? I mean, what are your thoughts about from our ability to predict and play the game and be precise? Do you have any further thoughts about finding the underlying circuitry? How far do you think we could go?
Look, we have a lot of people playing the game. I think that's our advantage. That we can. Oh, he said. He said we're playing a game of sorts in particle physics, or in general. do you think we'll succeed? Is that?
And that we're very good at manipulating the environment, but as you say, are we able to find the underlying circuitry that you can play the game without knowing that?
Part of the problem is we choose problems that we're probably likely to solve, right? And so the really hard question, like turbulence, what is turbulence? I mean, how are we ever going to get our heads around that? And then there certainly could be things that are happening on timescales in the universe. Suppose there are waves that there's only one of them, and it's going through the universe, and it has a period of 30 billion years. You know, how will we ever come to terms with even knowing it's there or knowing its effects? One thing is the universe is really, really big in time and size. And so to be living at a time when we figured it all out is probably the most depressing possibility that you can imagine. So you're right, there's lots out there.
We pick the game too.
Yeah, but we also pick the games. Yeah. Yes, sir. Sorry.
You used the phrase the expansion of the universe.
Yes.
You also talked about the use and possible limitations of language in describing knowledge.
Yeah.
I have read things which say that when people talk about the expanding of the universe, that people have the idea it's expanding into nothing or a void, but that is really wrong. How would you try to describe what is known to people like us?
Well, first of all, the idea of the expansion is that the fabric, if I can use the word, that space is being created between objects. So there's not really the necessity to think about it expanding into anything because it's creating space between the things that are already there. Okay. You also have to remember that the universe, as we see it now, because of this expansion, had a beginning, that in the sense that things were very, very close together, and the energy that we know is in the universe, as when you take it back, has profound effects by heating up the universe as you move it back, by compressing it. And so the universe becomes a very, very strange and different place, and we don't really know enough physics to go all the way back to times when densities were so much higher than anything that we've experienced here, and where gravity was so much larger than anything that we've experienced here. And so we have to depend on our ability to extrapolate into those domains. And the best analogy I can think of is consider a hurricane. And you see these winds, and you're out in the outer periphery of the hurricane, and as you're moving in, the winds are getting higher and higher and higher. And your mathematical model predicts that the wind velocity should go to infinity. But when you get there, it's quiet. Yes?
Thank you. Thanks so much for talking today. I had two questions for you. Actually, the first one is short and sweet. You said that language is the second most wonderful thing that evolution has given us. I was wondering what you thought the first one
Yes.
is. And my second question is that when you're speaking about cognitive closure or the closedness of our cognitive abilities,
Yeah.
you break it up into three separate types of people, right? You have Bailey, your dog, you have Barry, you, and you have Borgs, the cyborgs.
Yes.
And it looks like Bailey can certainly experience things, right? And perhaps Bailey feels some sort of romance about his life.
Absolutely.
All right, good. And you certainly can experience things.
Yeah.
It seems like you certainly have a romance towards this subject and other things, I'm sure, in your life. You also can describe things around you and even perhaps understand a few things, right? Now, we talk about the cyborgs, and it looks like in a conversation with a cyborg, you might even be able to have cyborgs that not only can describe things, but can understand things that we may not be able to understand. So what I'm interested in knowing is, you see how we have 4 romanticize that we haven't yet really been able to capture our own language.
Well, could you repeat the question? Sorry. Look, the question was about the first thing that evolution has given us. I'll answer that in a second. But the other was the possibility that the cyborgs could have an independent set of experiences, probably ones that we couldn't necessarily understand. I guess you have to, first of all, ask yourself, what is a cyborg? One possibility is that we just accommodate computers into ourselves, that we become more and more dependent on a computer, and that we could actually somehow link the computer software into the brain, and we become half machine, but we start off as human. The other is that the machine takes on some wet part for itself and becomes more animal. But it's also been said that even if a lion could speak, we wouldn't be able to understand it, because it has such a different view of the world, that its language would be so personal and so lion-esque or dog-esque that we're just not in a state of mind to know what it is that they're experiencing. Because the reason it works for us is that we all evolved together. So when somebody says they feel pain and we've felt pain, then we pretty much know it. But there are all sorts of examples where that doesn't work. You know, cilantro. I like cilantro. Somebody else says it tastes like soap. All right, well, what's going on there? I mean, we're using the same words, it's cilantro, but you have a different reaction to it in your mind and your body. And I can never know what that's like. I'm colorblind, you'll never know the joys of what it's like to be colorblind. All right.
The first question you didn't.
Yes, and the first question. What is the most wonderful thing that, and it's not romance, sorry, that evolution gave us? It's memory. You can do without sight, you can do without hearing, you can do without taste, but if you had no memory, you would have no sense of time, you would have no sense of past or present. It would be, you would be, I don't know what you'd be. You might be a plant, but you could still have your brain, and there's a very strange thing. There's a part of your brain that if it gets damaged, not only do you lose your short-term memory, you lose 2 years worth of memory before that, before it gets distributed out somewhere else. So don't have that part of your brain damaged, because you will then experience a life where you have no memory of the thing that just happened. You'll have past memories, but you'll be an entirely different person. So I think that memory is certainly the first step. You have to have that.
Okay, one
Yeah, forget
last
it.
question, and then I'm sure
Yeah, then forget
people
it.
can come up.
This is a hypothetical question. What if you took human civilization and astronomers and physicists in our civilization and took a hypothetical civilization, another species somewhere else in the universe, and both studying the universe, and their perception of the universe, would the tendency still be towards a similar outlook of the universe, or do you think it would be radically different the way they perceive the science, their perspective of what they're seeing in the universe?
Well, of course we feel that we're, and this is the view from nowhere part to the title. When we do physics, we don't think that we're in a special place in the universe or in time, but we are really very special. And you can't deny it. We don't know of any other civilizations, and we don't know of any other species that got to this stage. So there's got to be a perspective on this that is purely human. And you might want to ask, what sort of time scale over which do these other inhabitants of the universe live? If they lived for a million years per generation, they might have a very different perspective on what was going on in the universe. They might have a very different idea about continental drift, about global warming. So they might have a very different take on things. The thought is that physics is physics, but it is a creation, and it has evolved, and we've only been doing it for a few hundred years. So we might find things which will cause one of those great revolutions, and we'll suddenly, like antelope, everybody will go off in this direction with the new physics and say, silly creatures, back in the 20th century, what were they thinking? So, but you can't really premise your day-to-day life on the expectation that everything's wrong. but it may well be different.
Okay, let's thank our speaker for a very provocative talk.